Introduction to Operating Systems Fundamentals. Tasks and Goals of Operating Systems. An operating system is the central software that connects the physical parts of a computer with the programs you want to run. It acts as the primary controller that ensures every program gets the resources it needs to function properly without interfering with others. The primary purpose of this system is to hide the complexity of the hardware from the user and the software developer. Without this software layer, every single program would need to know exactly how to communicate with every specific type of processor, memory chip, and screen. By providing a standardized environment, the operating system allows programs to be written once and run on different physical machines. If you write a program to save a document, your program simply tells the operating system to save the data. The operating system then handles the specific electrical signals needed to write the data to the exact type of hard drive installed in your computer. To achieve this, the software must perform hardware abstraction, which means that the operating system creates a uniform layer over the diverse physical components. It manages the system resources, which include the central processing unit, the main memory, and input and output devices. To allow software to request actions from these resources, the operating system provides an application programming interface, which is a set of standardized commands that developers use to interact with the system safely. Operating system architectures: monolith, microkernel, and hybrid. Operating systems can be built in different ways depending on how much of the core software is given absolute power over the computer. The way these core parts are structured determines how fast the system runs and how safe it is from complete crashes. A system design that keeps all its components tightly together is faster, but significantly more vulnerable to complete failure than a system that separates its parts. When every component operates with maximum privileges in the same space, they do not need to pause to ask for permission to talk to each other, which speeds up processing. However, because they share the exact same space, a single error in any component can corrupt the entire system and force it to shut down. If a newly installed driver for a graphics card contains an error in a tightly integrated system, that single error will crash the entire computer, whereas in a separated system, only the graphics component would fail while the rest of the computer continues to work. The tightly integrated design is known as a monolithic architecture, where every part of the operating system runs with maximum privileges, which ensures high performance but reduces fault tolerance. To solve the vulnerability issue, the microkernel architecture was developed, which leaves only the most essential functions like memory management and communication with maximum privileges, while moving everything else to a restricted area. Because switching between the privileged and restricted areas takes time, modern computers often use a hybrid kernel architecture that combines the speed of the monolithic approach with the safety of the microkernel by keeping essential parts privileged but structuring them carefully to maintain stability. Execution modes: kernel mode versus user mode. Computers have built-in security levels to prevent normal programs from accidentally or maliciously destroying the system. The processor strictly controls what a program is allowed to do based on the security level it is currently running in. Restricting the access rights of normal software is essential to maintain the stability of the entire computer. If every program could interact directly with the physical memory or the processor, a simple programming mistake could overwrite critical system data. By forcing programs to operate in a restricted environment, the central system remains protected from faulty applications. If a text editing program attempts to read a memory location that does not belong to it, the processor detects this restricted access and immediately stops the text editor, which prevents the computer from freezing. The restricted environment where regular applications run is called the user mode, which ensures that programs cannot execute privileged instructions. When an application needs to access the hardware, the processor switches to the kernel mode, which is the highest privilege level where the operating system has unrestricted access to the entire physical hardware and memory. Processors implement these modes using physical security rings, where ring 0 represents the kernel mode and ring 3 represents the user mode. System calls versus library functions. Since normal programs operate in a restricted security level, they need a safe way to ask the main system for help when they want to perform tasks like reading a file. There is a specific pathway that allows this communication without breaking the security rules. Programs must use predefined entry points provided by the operating system rather than communicating with the hardware directly. Predefined entry points ensure that the operating system can check if the program has the right permissions to perform the requested action. This controlled handover changes the security level temporarily, performs the action safely, and then returns control and the results back to the program. When a program needs to display text on the screen, it triggers a predefined entry point. The system takes over, verifies the request, puts the text on the screen using its own secure code, and then lets the program continue its work. These predefined entry points are called system calls, which initiate a mode switch from user mode to kernel mode so the operating system can execute privileged commands. Because system calls are highly dependent on the specific physical hardware, developers usually use library functions instead, which are portable software routines that run in user mode and internally prepare and execute the complex system calls. Process and thread concept. Definition and differences: process versus thread, single versus multi-threading. A program running on a computer needs to be managed securely so it does exactly what it was written to do. The system separates the overall container that holds everything the program needs from the actual sequence of instructions that the computer reads and executes. Separating the container from the execution steps makes computers much more efficient at doing multiple things at once. When an application needs to perform several tasks at the same time, it does not need to duplicate all its memory and resources. Instead, it can start multiple separate sequences of instructions that all use the exact same shared container. If a text editing application checks spelling while you type, it uses one sequence of instructions to read your keystrokes and another to check the dictionary within the very same memory space without needing to load the dictionary twice. The overall container that holds the running program and its resources is called a process. The active sequence of instructions executed by the central processing unit is called a thread. When a process uses only one single sequence of instructions, it operates in single threading mode. When a process launches multiple concurrent sequences of instructions that share the same memory space to perform parallel tasks, it utilizes multi-threading. Resource management: process image address space and process control block versus thread control block. Every running application requires a specific amount of memory and detailed records about its current status to function correctly. The central system bundles all this data and management information together so it always knows exactly where the application is located and what it is currently doing. Bundling all related memory and status information into standardized data packages is strictly necessary to keep applications isolated and secure from each other. By organizing every running application into its own strictly defined area, the system can easily track who owns which piece of data and prevent one application from accidentally overwriting the data of another. When an email application and a web browser are open at the same time, the system maintains separate records for each so that if the web browser crashes, its specific data package is removed without affecting the emails currently held in the other data package. All the information required to run an application, including its program code and variables, is stored in the process image, which resides in a specific memory area called the virtual address space. To manage the attributes of this container, the system uses a process control block, which acts as a central data record for the specific process. For managing the individual execution sequences within that process, the system uses a thread control block, which stores specific details like the current position in the instruction sequence and the processor register values for that exact thread. State models: 5-state model and 7-state model, including all state transitions. Running programs do not constantly use the processor because they often have to wait for external events to happen. The system keeps track of what phase of activity or waiting a program is currently experiencing to decide what should run next. Classifying programs into specific operational states maximizes the utilization of the processor. When the system knows exactly which programs are ready to do work and which ones are stuck waiting for data, it can immediately assign the processor to a ready program instead of sitting idle. If a calculation program needs a file from the hard drive, it enters a waiting phase while the disk spins. During this waiting phase, the system immediately gives the processor to a music player program so the music continues playing without any interruption. The basic life cycle of a process is described by the 5-state model. A process starts in the new state when it is created and moves to the ready state once the system admits it and resources are available. The system scheduler then moves it to the running state where it actually uses the central processing unit. If the process has to wait for an event like user input, it transitions to the blocked state and only returns to the ready state when the event occurs. Once the process finishes its task, it enters the exit state. Because physical memory is limited, the system sometimes moves entire suspended processes to the hard drive, which requires the 7-state model. This expanded model adds a suspend ready state for processes that are ready but stored on disk and a suspend blocked state for processes that are both waiting for an event and moved to the disk. Interruptions and process switches causes hardware interrupts, traps system calls and procedure. The main processor must occasionally stop what it is currently doing to attend to more urgent matters or to give other programs a fair turn. This controlled stopping and switching ensures that the computer responds quickly to new inputs and remains completely stable. Forcing a program to temporarily halt its execution is essential for maintaining control over the entire system. Without the ability to pause programs forcefully, a single frozen application could keep the processor forever, preventing the user from doing anything else and stopping the system from processing vital background tasks. When a user presses a key on the keyboard to close a frozen program, the physical keyboard sends a signal that instantly pauses the frozen program, allowing the system to process the key press and force the application to shut down. The events that force the central processing unit to pause a process are called interruptions. External events like a timer finishing or a keyboard press generate hardware interrupts. If the process itself performs an illegal action like dividing a number by 0, it generates a software exception known as a trap. When a process actively requests a service from the operating system like reading a file, it executes a system call. Any of these events trigger an interrupt service routine which changes the security level to kernel mode and often leads to a process switch where the system saves the state of the currently running process and loads the state of the next process to be executed. Task type programming: process creation, fork, and termination in C. When writing software, developers need commands to start new applications directly from their code and to safely shut them down when their work is done. There is a specific method in the programming language to clone an existing program so that two identical versions run side by side. Cloning an already running program is a highly efficient way to handle new incoming tasks quickly. Instead of building a completely new environment from scratch, the system simply creates an exact duplicate of the current program in memory, allowing the duplicate to handle the new task while the original goes back to waiting for more work. When a network server receives a request for a web page, the main server program clones itself. The newly created clone handles sending the web page to that specific user, while the original server program immediately goes back to listening for requests from other users. In the C programming language, the function used to clone a process is called fork. When fork is executed, it creates a new child process that is an exact copy of the parent process. The system tells the parent process the unique process identification number of the child, while it tells the child process that its result is 0, allowing the execution paths to diverge. When a process has finished its execution or encounters a severe error, it undergoes termination, either voluntarily by reaching the end of its code or involuntarily, if it is killed by the operating system due to a critical failure. Task type programming: thread creation, thread create, and thread join in C. Sometimes a program needs to do multiple things at the same time within its own shared space without creating a completely separate cloned program. Developers use special commands to spin off new active sequences that run concurrently inside the exact same application. Launching concurrent sequences within the same application greatly simplifies data sharing during complex operations. Because these concurrent sequences automatically share the same memory space, they can instantly read and modify the exact same variables without needing complex and slow communication channels. An image editing program applying a complex mathematical filter can spin off 4 separate sequences to process 4 different corners of the image at the same time. Since they all operate in the same memory, they can read the original image data directly and seamlessly combine the finished result into one picture. To achieve this, in the C programming language, developers use the Portable Operating System Interface Thread library. The function thread create is called to generate and start a new thread, pointing it to a specific subroutine to execute. Because the main program must ensure all parallel tasks finish before shutting down, it uses the function thread join, which pauses the main sequence and waits blockingly until the specified thread completes its assigned subroutine. Process scheduling, central processing unit scheduling. Fundamentals, job scheduling long-term versus central processing unit scheduling short-term. A computer system must constantly decide which programs are allowed to run and when they get to use the processor. Dividing this planning into two separate timeframes ensures the system does not become overwhelmed by too many active applications. If too many programs are loaded into the main memory at once, the system cannot function effectively. Therefore, one mechanism controls the overall admission of programs into the system, while another mechanism rapidly switches the processor between the already admitted programs. If 20 users try to start massive calculations on a server simultaneously, the system only allows 5 calculations to enter the active pool to preserve memory. While those 5 are active, the system rapidly switches the processor among them, so they progress together while the remaining 15 calculations wait outside the active pool. The mechanism deciding which new tasks are admitted into the system is called job scheduling or long-term scheduling. Once tasks are admitted and ready to run, the central processing unit scheduling or short-term scheduling takes over to rapidly determine which specific program receives the processor next. Terminology: central processing unit, burst input, output burst, and scheduling points. Programs alternate between actively calculating data and pausing to wait for external hardware. The system must monitor these alternating phases and know exactly when it is safe to reassign the processor to another program. A processor cannot do any useful work if the current program is simply waiting for a hard drive to fetch a file. The system must detect these waiting periods and specifically defined events to immediately switch to another program, ensuring the processor is never idle. A text editing program calculates the layout of a page and then pauses to wait for the user to press a key on the keyboard. During this waiting phase, the system reassigns the processor to an antivirus program that needs to scan files, so work continues while the text editor waits. The phase where a program actively uses the processor for calculations is called a central processing unit burst. The phase where it pauses for external data is called an input-output burst. The specific moments when the operating system intervenes to reassign the processor, such as when a program blocks or finishes, are known as scheduling points. Criteria for good scheduling: fairness, efficiency, throughput, waiting time, and turnaround time. A system must evaluate how well it manages the execution of programs based on specific performance targets. Balancing the needs of the system against the needs of the individual users requires clear measurement criteria. Different environments require different priorities, where a server might need to finish as many background tasks as possible, while a desktop computer needs to respond to user clicks instantly. It is mathematically impossible to perfectly optimize all these conflicting parameters at the exact same time. A background database server prioritizes completing a high number of data updates per hour, even if an individual update takes slightly longer. In contrast, a user interacting with a graphic interface expects the application to react to a mouse click instantly regardless of the overall system throughput. To evaluate performance, the system relies on criteria such as fairness, which ensures every process gets a just share of processor time, and efficiency, which measures how fully the processor is utilized. Throughput counts how many total jobs are completed in a specific interval. User-oriented criteria include waiting time, which is the total duration a process sits idle in the ready queue, and turnaround time, which measures the complete span from a process entering the system until its final termination. Categories: non-preemptive versus preemptive scheduling. There are two fundamental approaches to how forcefully a system controls the processor. The system can either politely wait for a program to release the processor, or it can forcefully take it away. Allowing a program to run uninterrupted is simple and efficient, but highly dangerous if the program freezes or enters an endless loop. Forcefully interrupting programs ensures that all active applications get a fair turn and the system remains highly responsive. If a simple batch processing system is printing salaries, it runs the printing program until the job is completely finished. In a modern desktop computer, the system forcefully stops the video player every few milliseconds to let the network program download a file, ensuring both video and download progress together. The polite approach is called non-preemptive scheduling, where the system never removes the processor from an active process until that process voluntarily blocks or finishes. The forceful approach is called preemptive scheduling, where the operating system uses hardware timer interrupts to actively pause a running process and assign the processor to another ready process. Scheduling algorithms. A computer relies on specific mathematical rules to decide the exact order in which waiting programs are executed. These rules ensure the system operates predictably according to the desired performance targets. Without strict mathematical rules, the operating system would have to guess which program is most important, leading to chaos and frozen applications. Different rules are specifically designed to prioritize different types of computer usage. If a server is processing thousands of identical calculations overnight, it uses a rule that maximizes total data processed. If the same server is used by office workers during the day, it switches to a rule that ensures extremely fast responses to keyboard inputs. The mathematical logic determining the sequence of execution is called a scheduling algorithm. The operating system uses these algorithms to repeatedly evaluate the ready queue and select the most optimal process for the next central processing unit burst. First come, first serve. The most basic way to order tasks is to serve them exactly in the order they arrive. Processing tasks strictly sequentially is very easy to manage, but can cause severe delays for newer tasks. If a massive task arrives first, it will occupy the processor for a long time, forcing all subsequent smaller tasks to wait indefinitely. This creates a bottleneck that drastically increases the average waiting duration for the entire system. If a massive video rendering process arrives just a fraction of a second before 10 tiny text saving processes, the 10 text processes must wait an hour for the video to finish. The small tasks are delayed heavily because the long task refuses to yield. This simple mechanism is known as first-come, first-serve scheduling. The scheduler simply places each new process at the back of the ready queue, and the dispatcher assigns the processor to the process at the front without any preemptive interruption. Shortest job first. To reduce the average time tasks spent waiting, the system can execute the quickest tasks before the longer ones. Sorting tasks by their length allows many small tasks to finish rapidly. Getting small tasks out of the way decreases the total number of waiting tasks, which drastically lowers the average waiting duration. However, the system must somehow predict how long each task will take to execute. If the system has a 5-minute rendering task and a 1-second text-saving task, it runs the text-saving task first. The text task finishes almost instantly, and the rendering task only waits 1 second instead of the text task waiting 5 minutes. This strategy is called shortest job first scheduling. The scheduler evaluates the estimated length of the next central processing unit burst for each process and always selects the process with the smallest value. Round robin and virtual round robin. To ensure every program gets regular attention, the system can assign a strict maximum time limit to each task. Passing the processor around in a circle guarantees that no single program monopolizes the computer. Rotating the processor in small increments creates the illusion that many programs are running simultaneously. However, programs that frequently pause to read data lose their assigned time and are severely disadvantaged compared to programs that constantly calculate. If a music player gets 10 milliseconds but uses only 2 milliseconds before waiting for the hard drive, it loses its remaining 8 milliseconds. A mathematical calculator uses its full 10 milliseconds every turn, thereby advancing much faster than the music player. The basic rotational method is called round-robin scheduling, where each process gets a fixed time slice known as a quantum. To fix the disadvantage for pausing programs, the system uses virtual round-robin, where processes that block early are moved to an auxiliary ready queue upon waking to receive preferential scheduling. Highest response ratio next. A system can balance the priority of short tasks against the unfairness of making long tasks wait forever. By calculating a dynamically changing score, the system can favor short tasks while gradually increasing the priority of long tasks over time. As a long task waits, its score continually grows until it eventually surpasses the scores of newer shorter tasks. This mathematical approach guarantees that even the longest tasks will eventually reach the top of the priority list. A heavy calculation task waits in line while many quick tasks bypass it. After an hour of waiting, its calculated score becomes so high that the system finally halts the quick tasks and allows the heavy calculation to proceed. This non-preemptive algorithm is called highest response ratio next. The system calculates a response ratio by adding the total waiting time to the estimated execution time and dividing the result by the estimated execution time, selecting the process with the highest resulting ratio. Priority scheduling and multilevel feedback scheduling, including anti-aging. Modern systems group tasks into different levels of importance and adjust these levels based on the behavior of the tasks. Programs that consume too much processor time are demoted to lower levels to make room for interactive programs. Separating programs into different queues allows the system to enforce strict priority rules. By automatically lowering the priority of heavy calculators, the system naturally favors quick interactive tasks but must actively prevent demoted tasks from being forgotten entirely. A system assigns high priority to a keyboard reading process and lower priority to a background virus scan. If the virus scan runs too long, the system drops it to an even lower priority level, but if it is stuck there for an hour, the system manually raises its priority back up. Assigning distinct importance levels is known as priority scheduling. Implementing this with multiple queues where processes drop to lower queues after using their full quantum is called multilevel feedback scheduling, while raising the priority of processes that have waited too long is called anti-aging. Fair share scheduling. Sometimes the processor should be divided among users rather than individual programs. This ensures that one user running many programs does not unfairly dominate the system against a user running only one program. If the system treats every program equally, a user who launches 50 programs will monopolize the processor, leaving almost nothing for a user who launched only one. By assigning resource percentages to user groups, the system maintains a fair balance between the users themselves. User A runs 1 calculation and user B runs 9 calculations. Instead of giving user A 10% of the processor, the system gives user A 50% for their single calculation and user B 50% divided among their 9 calculations. This resource allocation method is called fair share scheduling. The central processing unit time is divided into specific percentages called shares, which are assigned to process groups or individual users rather than being distributed evenly among all active processes. Task type drawing of Gantt charts and calculation of waiting and turnaround times for given processes. To understand and predict how different scheduling rules affect program execution, we can visualize the exact timeline of processor assignment. Drawing a timeline makes it easy to calculate exactly how long each program waited and how long it took to finish completely. A graphical representation clarifies the sequence of events, showing exactly when programs arrive, when they execute, and when they finish. From this timeline, we can extract precise numerical values to compare the efficiency of different scheduling rules. By sketching a timeline box for a task that arrives at second 0 but only starts running at second 5 and finishes at second 10, we can clearly see the task waited for 5 seconds, and its total duration from start to finish was 10 seconds. The visual timeline used to represent scheduling is called a Gantt chart. By analyzing the intervals on this chart, we calculate the waiting time by adding all the periods a process spent in the ready state, and we calculate the turnaround time by subtracting the arrival time from the final termination time. Interprocess communication synchronization and mutual exclusion. Need for interprocess communication and the problem of race conditions. Programs running on a computer often need to work together to complete complex tasks. Because the main system strictly isolates every running program to prevent crashes, they cannot simply look into the memory of other programs. To enable teamwork, the system must provide secure channels for programs to exchange data and coordinate their actions. If completely isolated programs could not exchange results or tell each other when they finish a specific step, it would be impossible to divide a large calculation across multiple programs. If one program constantly reads temperature sensors and another program saves these readings to a hard drive, the first program must have a secure way to hand the temperature numbers over to the second program. The secure channels and coordination methods provided by the operating system are known as interprocess communication. When multiple programs try to modify the exact same shared data at the exact same time without coordinating their turns, they create a race condition. A race condition means the final result is unpredictable because it depends entirely on which program reached the data a fraction of a second faster. Essential interprocess communication mechanisms, shared memory signals pipes and message queues. The operating system offers different methods for programs to exchange information depending on how much data they need to send and how fast it must arrive. Some methods send simple notifications while others move large amounts of data. Providing a variety of exchange methods ensures that developers can always choose the most efficient tool for their specific software problem. A mechanism designed to send a single emergency stop command would be far too slow to transfer a high-resolution image, whereas a mechanism built for massive data transfers would be overly complicated for a simple stop command. A user clicking a stop button uses a tiny instant notification to halt a calculation program, whereas a video editing program uses a massive direct data transfer to hand over a video frame to a display program. The fastest transfer method is shared memory, where the operating system allows two processes to access the exact same physical memory area. For simple notifications, the system uses signals which are asynchronous alerts that interrupt a process to tell it that a specific event occurred. When programs need to send continuous streams of bytes in one direction, they use pipes which act as unidirectional data pathways connecting related programs. 4 structured data programs use message queues, where the sender deposits discrete data packages into a list, and the receiver collects these packages one by one. Critical sections and the concept of mutual exclusion. When multiple programs share data, they must take turns modifying it to avoid destroying the information. There are specific parts of a program where it actively changes shared data, and these parts require strict supervision. Programs must be physically prevented from modifying the same shared data at the exact same time. If 2 programs read a value, add 1 to it, and write it back simultaneously, they might both read the original value and write back the same increment value, resulting in one addition being completely lost. If a parking garage system uses one program to count cars entering and another to count cars leaving, and both try to update the total free spaces simultaneously, the final count will be incorrect, leading to a full garage accepting more cars. The specific sequence of instructions where a program accesses shared resources is called a critical section. To prevent data corruption, the system enforces mutual exclusion, which is a strict rule ensuring that if one process is currently executing its critical section, absolutely no other process is allowed to enter its own corresponding critical section. Solution approaches for mutual exclusion: busy waiting versus blocked waiting. To enforce the rule that only one program can access shared data at a time, the system uses access controls. Programs must check these controls before proceeding, and if the access is denied, they must wait. The method a program uses to wait for access drastically affects the overall performance of the entire computer. A program can either repeatedly check the access control in a continuous loop, which consumes immense processor power, or it can put itself to sleep and let the operating system wake it up when the access is granted, which saves power but takes a little time to coordinate. If a program waiting to write to a file constantly asks the system if the file is free, it uses up processor energy that a completely different music playing program needs to decode audio, causing the music to stutter. Continuously checking an access variable in a tight loop is called busy waiting, or using a spin lock which keeps the process in the running state while doing no useful work. To prevent this waste, developers prefer blocked waiting, where the operating system moves the waiting process into the blocked state, suspending it entirely until the resource is freed. Synchronization tools: Semaphores and Mutexes. The operating system provides standardized control mechanisms to safely manage access to shared resources without wasting processor time. These control mechanisms automatically handle the complex task of suspending programs and waking them up. Using standardized system tools for managing access is far safer than developers trying to write their own checking mechanisms. Standardized tools are built directly into the operating system core using special indivisible hardware instructions, ensuring that 2 programs cannot accidentally check and claim an open resource at the exact same microscopic fraction of a second. When 10 different programs try to claim a single available printer simultaneously, the system control mechanism guarantees that exactly 1 program gets the permission, while the other 9 are instantly put to sleep. The most common mathematical tool for this is a semaphore, which is a special variable that manages access using indivisible wait and release operations. A counting semaphore is initialized to a number greater than 1 to manage multiple identical resources, while a binary semaphore is initialized to 1 to enforce strict mutual exclusion. When developers write concurrent threads inside a single application, they use a mutex, which is a specialized lock exclusively designed to provide mutual exclusion for threads sharing the same memory space. Task-type programming protection of critical sections and implementation of synchronization scenarios. Developers must write specific code to implement these access rules when building software that handles continuous data production and consumption. This ensures the producing part does not overwhelm the system and the consuming part does not try to read empty data. A properly programmed data pipeline must automatically pause the producing part when the storage is full and automatically pause the consuming part when the storage is empty. If the producing part ignores the storage limit, it will overwrite data that has not been read yet, and if the consuming part ignores the empty state, it will process old or invalid data multiple times. A program reading a temperature sensor thousands of times a second must automatically pause if the program analyzing the temperature data falls behind, preventing the analyzing program from receiving corrupted partial temperature readings. This common software pattern is called the producer-consumer problem. To solve it in the C programming language, developers use the Portable Operating System Interface Thread library to create mutexes protecting the critical sections where data is written and read. They also use Portable Operating System Interface message queues or counting semaphores to implicitly track how many spaces are full and how many are empty, automatically triggering blocked waiting when limits are reached. Memory management. Fundamentals, memory pyramid, and concept of multiprogramming. A computer contains different types of data storage that vary in speed, size, and cost. To run programs efficiently, the system must balance fast, expensive storage against slow, cheap storage while keeping multiple programs ready. The processor works incredibly fast and cannot afford to wait for data to arrive from a slow storage drive, otherwise it would sit idle most of the time. If a calculation program waits for data from a slow hard drive, the system immediately switches the processor to a background music program, ensuring continuous operation. The hierarchy of storage speeds and capacities is called the memory pyramid, which ranges from tiny, extremely fast processor registers down to massive slow secondary storage. To keep the processor busy, the system uses multiprogramming, which means it loads several programs into the main memory simultaneously so it can switch between them instantly when one program has to wait. Partitioning static versus dynamic, including fragmentation. Early systems divided the main memory into distinct sections to hold multiple programs at once. Dividing memory into fixed or flexible sections creates inefficient gaps where memory is wasted. If the sections are fixed, a small program leaves unused space inside its assigned section, and if the sections are flexible, removing finished programs leaves scattered and used gaps between active programs. If a large memory section is assigned to a tiny text editor, the remaining space in that section cannot be used by a massive video editing program, resulting in wasted capacity. When memory is divided into fixed sizes, it is called static partitioning, which causes internal fragmentation because unused space remains trapped inside the assigned sections. When memory is assigned exactly according to program size, it is called dynamic partitioning, which avoids internal waste but causes external fragmentation because starting and stopping programs leave small unusable gaps scattered throughout the main memory. Paging and virtual memory definitions, pages, frames, and page tables. Modern computers separate the memory a program thinks it has from the actual physical memory chips installed in the machine. Dividing memory into uniform standardized blocks allows the system to run programs that are collectively larger than the physical memory. Because the system can move these uniform blocks seamlessly between the fast physical memory and the slow storage drive, it only needs to keep the actively used blocks in the fast memory. A heavy video game might require 10 gigabytes of memory, but the system only loads the blocks containing the current level into the fast memory, while leaving the other levels on the hard drive until the player reaches them. The overall memory space a program sees is called the virtual address space, which is divided into standardized blocks called pages. The physical main memory is divided into identical standardized blocks called frames. To keep track of which page is currently loaded into which frame, the operating system maintains a page table for every single process. Task type conversion of virtual into physical addresses. When a program wants to read a specific piece of data, the system must calculate exactly where that data is physically located in the computer. The system must mathematically translate the location requested by the program into the actual physical location in the memory chips instantly. Programs only know their own isolated memory layout and have absolutely no knowledge of where the operating system has physically placed their data. When a program asks for the first letter of a document at its own position 1000, the system calculates that this specific part of the document is currently stored in physical memory at position 50,000. The central processing unit uses a specialized hardware component called the memory management unit to perform this address translation. The requested virtual address is split into a page number and an offset where the page number is replaced by the actual physical frame number found in the page table, while the offset, which is the exact position within the block, remains completely unchanged. Hardware support translation, Lookaside buffer, and multilevel page tables for acceleration and memory optimization. Translating addresses for every single instruction takes time, and the lists keeping track of these addresses consume massive amounts of memory. The system must use specialized high-speed hardware memory and layered tracking lists to keep the computer running fast and efficiently. If the system had to read the massive tracking list from the main memory for every single calculation, the computer would slow down drastically, and if the tracking list was kept in one single piece, it would leave almost no room for actual programs. If a program processes an image pixel by pixel, the specialized hardware remembers the location of the image block instantly for the second pixel without asking the main memory again, while the layered lists ensure that tracking data for unused image parts is not loaded at all. To accelerate the translation process, the processor uses a tiny, extremely fast memory called a translation lookaside buffer, which caches the most recent translations based on the principle of locality. To save physical memory space, the system uses multilevel page tables which split the massive tracking list into a hierarchy, allowing the operating system to load only the actively used parts of the table into the main memory. Page replacement algorithms, replacement policies. When the fast physical memory is completely full and a program needs new data, the system must decide which old data to remove. Choosing the right block of data to remove is critical for the overall speed of the entire computer. If the system removes a block of data that a program needs again, immediately the computer will waste immense amounts of time constantly moving the same data back and forth from the slow storage drive. If the system removes the main dictionary file while a user is typing a document, the computer will freeze on every new word because it has to fetch the dictionary from the slow hard drive over and over again. When a program requests a page that is not in the physical memory, it causes a page fault, which forces the operating system to execute a replacement policy. This policy is a mathematical algorithm that selects an optimal frame to evict, ensuring that the most frequently used data remains in the fast physical memory. Optimal strategy, least recently used, first in, first out. There are different mathematical rules to determine which memory block should be removed, ranging from theoretical perfection to simple chronological order. Finding the absolute perfect block to remove is impossible, so systems rely on chronological rules that are either too slow or too inaccurate. A computer cannot predict the future to know exactly what data will be needed next, and keeping exact timestamps of every single data access slows the processor down massively. If the system simply removes the oldest loaded web page, it might accidentally remove the main search engine page the user checks every minute because it was loaded first, while keeping a newly loaded advertisement page. The optimal strategy replaces the page that will not be used for the longest time in the future, which is impossible to implement but serves as a theoretical benchmark. The least recently used algorithm replaces the page that has not been accessed for the longest time in the past, which is highly accurate but creates too much processing overhead. The first in first out algorithm simply removes the oldest page, which is very easy to implement, but often removes heavily used pages, causing severe performance drops. Clock second chance, not recently used, not frequently used, aging working set clock. To balance speed and accuracy, modern computers use clever tracking methods that observe how programs behave without slowing them down. By using simple hardware flags and periodic checks, the system can efficiently guess which memory blocks are no longer needed. Instead of recording the exact millisecond of every access, the system only notes if a block was touched recently or modified, which provides enough information to make smart removal decisions instantly. When the memory is full, the system checks a circular list of loaded documents and skips the document the user just scrolled through, focusing instead on a background document that has not been touched in an hour. The clock or second chance algorithm uses a referenced bit set by the hardware, giving recently accessed pages a second chance while moving a pointer in a circle. The not recently used algorithm categorizes pages by combining the referenced bit with a modified bit to avoid evicting pages that require time-consuming saves. The not frequently used algorithm estimates usage by adding the referenced bit to a counter periodically, and the aging algorithm improves this by shifting the counter to slowly forget older accesses. Finally, the working set clock algorithm efficiently tracks the active working set of a process based on execution time, replacing only those pages that have fallen outside the current active time window. Task type determining example scenarios of page replacements, counting page faults entering main memory frames. To evaluate how well these different removal rules perform, developers trace the exact sequence of data requests step by step. Manually calculating the sequence of memory loading and removal is essential to prove the efficiency of a chosen rule. By simulating the memory capacity and applying the mathematical rule to a predefined list of requests, one can count exactly how many slow storage accesses would occur. By tracking a sequence of numbers on paper with a limit of 3 slots, one can clearly see that a simple oldest first rule causes 10 slow loading events, while a smartest choice rule only causes 5 slow loading events. When solving these scenarios, one tracks the chronological access sequence to determine the content of each main memory frame after every step. By applying the specific algorithmic rules, one identifies every page fault which occurs when the requested page is missing and records the exact eviction decision to calculate the total performance overhead. Input-output management and file systems. Principal input-output types: programmed, polling, interrupt-based, and direct memory access. A computer must constantly communicate with external devices like keyboards or hard drives to receive new data and output results. The way the central processor interacts with these devices determines how much time it wastes waiting for the slow mechanical parts to finish their work. Forcing the central processor to constantly monitor a slow device is extremely inefficient compared to letting the device notify the processor only when it is completely ready. External devices operate much slower than the processor, so if the processor continuously asks if data is ready, it uses all its calculation cycles for asking and cannot perform any other useful work during that time. If a processor requests a file from a slow hard drive and continuously checks the drive status, it completely freezes the entire computer, whereas if it sends the request and immediately switches to running a background virus scan, the user experiences a completely smooth system. The inefficient method where the processor continuously checks the device status in a loop is called programmed input-output or polling. To solve this waste of time, systems use interrupt-based input-output, where the processor issues a command and switches to another ready process until the device sends a hardware signal to get attention. For transferring massive amounts of data, the system uses direct memory access, where a specialized controller moves the data directly into the main memory without involving the central processing unit at all. Interrupt management hardware interrupts, interrupt controller, and interrupt service routine. When an external device finishes its work, it must somehow tell the main processor to stop what it is currently doing and process the newly arrived data. The computer needs a strict hardware mechanism to grab the attention of the processor instantly and securely. Without a central hardware component to manage all incoming signals from connected devices, the processor would be completely overwhelmed by chaotic simultaneous notifications. Multiple devices might finish their tasks at the exact same fraction of a second, so a dedicated electronic component must collect these incoming signals, prioritize them, and hand them to the main processor one by one in an orderly fashion. If a user presses a keyboard key and a network card receives an important message simultaneously, a central manager ensures the keyboard press is processed first, so the typing feels instant, while the network message waits a microsecond longer. The electrical signals generated by external hardware to pause the running processor are called hardware interrupts. A specialized electronic chip called the interrupt controller detects these events, prioritizes them, and sends a specific identification vector number to the central processing unit. Upon receiving this number, the operating system changes to the highest privilege level and executes a specific software function called the interrupt service routine, which handles the data transfer for that exact device while blocking other normal programs. File System Architecture Layer Model. Saving and reading files requires complex coordination between the user program and the physical storage disk. The operating system divides this massive task into several stacked software levels where each level performs one specific part of the job. Separating the file handling into independent software layers makes it possible for a single program to save data on entirely different types of physical storage without ever changing its own code. By putting the complex physical commands at the bottom and a simple standardized interface at the top, the application only needs to learn one simple way to save a file, while the lower layers handle the specific electrical signals for the actual hardware. A text editing program uses the exact same command to save a document to an internal hard drive or an external flash drive, because the specialized software at the bottom automatically translates the standard save command into the correct electrical impulses for the respective physical device. The standardized commands used by the text editor reside in the logical file system input-output layer, which provides the application programming interface for all user programs. Below this, the input-output supervisor coordinates access rights and manages the file status, while the physical file organization layer translates the continuous data into standardized storage chunks. Finally, the lowest layer, called the device driver, communicates directly with the physical hardware components using specific electrical signals. Physical file organization, mapping of files to logical blocks. When a user saves a massive file, the operating system does not write it to the disk as one single giant piece of data. Instead, it chops the continuous file into many small standardized pieces before writing them to the storage. Slicing massive files into uniform pieces allows the operating system to utilize every empty space on the storage drive highly efficiently. If files were saved as single massive chunks, the system would constantly have to search for completely empty areas that perfectly fit the specific size of the entire file, leaving many small empty spaces completely unused. If a user saves a massive movie file, the system drops the first part of the movie into a small gap left by a deleted text document, and the second part into another gap, completely filling the drive without wasting any available storage space. The specific mathematical process of translating the continuous file content into uniform data packages is called the mapping of files to logical blocks. The operating system manages these logical blocks, constantly tracking exactly which ones are free, occupied, or defective, while the hardware-specific device drivers later translate these logical blocks into physical sectors on the actual disk hardware. Block allocation types: contiguous, chained, and indexed. Because a single file is split across many different pieces, the operating system needs a tracking method to remember exactly which pieces belong to which file, and in what exact order they must be read. The tracking method used to link these pieces drastically determines how fast the system can jump to a specific part of a massive file. If the system only knows where the first piece is located, and each piece merely points to the next one, it must sequentially read every single piece just to find the very end of the file. If a user wants to jump directly to the middle of a massive audio recording, a system that stores a master list of all piece locations can instantly start playing the middle part, whereas a system relying on sequential pointers must silently read the entire first half before it can play the requested section. Storing all pieces directly next to each other is called contiguous allocation, which is incredibly fast but leaves unusable fragmented gaps on the disk. Storing pieces anywhere and having each piece point to the following one is called chained allocation, which prevents storage gaps but makes random jumps very slow. Modern operating systems use indexed allocation, where a central table stores the exact locations of all individual blocks belonging to a specific file, allowing instant access to any part without wasting storage space. Task-type programming, using file operations in the C programming language for binary and text files, including random access. When software developers write programs, they use specific commands to create read and write data to the hard drive. They must choose whether to save the data as human-readable characters or as compact internal computer numbers. Storing data as pure internal computer numbers is far more efficient than storing it as human-readable text when a program needs to process massive amounts of information rapidly. Human-readable text requires additional translation steps and variable amounts of space for each number depending on its length, whereas computer numbers use a strict standardized size that the processor can read instantly without any translation. If a program saves the number 1,000,000 as text, it writes 7 separate characters taking 7 bytes, but if it saves the same number in internal computer format, it strictly uses 4 bytes, allowing the program to read thousands of numbers flawlessly without searching for separation spaces. Data saved as human-readable characters is called a text file, which is processed using formatted commands like file scan format and file print format. Data saved in the exact format the processor uses internally is called a binary file, which is read and written using direct memory copy commands like file read and file write. Before any operation, the developer must use the file open command to establish a connection, and when they need to jump to a specific location instantly without reading everything, they use the file seek command to move the internal address pointer.